Hello everyone, welcome back to the video lectures on digital signal processing, and we are studying about the topic Discrete Fourier Transform and its properties. This is lecture 6. So in this video lecture we are going to study about the properties of DFT. There are 12 properties of DFT: periodicity, linearity, circular symmetries, symmetry property of DFT, circular convolution, time reversal, circular time shift, circular frequency shift, complex conjugate property, circular correlation, multiplication of two sequences, and Pascal's theorem. So one by one we are going to prove these properties in this video lecture. First is the periodicity property. So according to the periodicity property, if x of n and x of k are n-point DFT pairs, that means x of n is the time domain sequence and you apply n-point DFT to convert it into x of k in the frequency domain, then x of n plus n is equal to x of n for all values of n, and x of k plus n is equal to x of k for all values of k. So periodicity property indicates that x of n is periodic with a period of capital N. Similarly, x of k is also periodic with a period of capital N. So we take the formula of DFT. X of k equal to summation n is equal to 0 to n minus 1 x of n w n to the power of nk. Now here we replace k with k plus n, then we have x of k plus n is equal to summation n is equal to 0 to minus 1 n minus 1 x of n w n to the power of n into k plus n. So this is equal to summation n is equal to 0 to n minus 1 x of n. We will expand this, we will get w n to the power of nk into w n to the power of n capital N. We know that w n to the power of n capital N is equal to 1. So this is equal to summation n is equal to 0 to n minus 1 x of n w n to the power of nk, and which is equal to x of k. So we have proved the second one, that is x of k plus n is equal to x of k. Similarly, if we take the IDFT, that is x of n equal to 1 by n summation k equal to 0 to n minus 1 x of k w n to the power of minus nk. We have taken the IDFT formula. Here we had taken the DFT formula, and now we replace n with n plus n. So we get x of n plus n is equal to 1 by n summation k equal to 0 to n minus 1 x of k w n to the power of minus n plus n into k. So this is 1 by n summation k equal to 0 to n minus 1 x of k. Now we will expand this, w n to the power of minus nk into w n to the power of minus capital Nk. Now this is 1, so we'll get 1 by n summation k equal to 0 to n minus 1 x of k w n to the power of minus nk. W n to the power of minus nk is e to the power of j 2 pi nk by n. Cancel, so you get e to the power of j 2 pi k, which is cos 2 pi k plus j sin 2 pi k. We know cos 2 pi k is 1 and sin 2 pi k is 0. So wn to the power of minus n k is 1. Now what is this 1 by n summation x of k wn to the power of minus n k? It is x of n. So from this we have proved the first one, that is x of n plus capital N is equal to x of n. And here it was x of k plus n is equal to x of k. This is periodicity property of DFT. Next we have linearity property. Now let us say we have x1 of n. The DFT is x1 of k endpoint, and we have x2 of n. Once again the endpoint DFT is x2 of k. Then for any real valued or complex valued constants a1 and a2, a1 x1 of n plus a2 x2 of n, when we perform endpoint DFT, we should get a1 x1 of k plus a2 x2 of k. That is weighted superposition of inputs. When you apply DFT, you will get weighted superposition of individual DFTs. So I'll just write this as y of n and this frequency domain signal as y of k. So if I apply DFT, so y of k is DFT of y of n, or this is DFT of a1 of n of n plus a2 x2 of n. So you just take the formula, summation is equal to 0 to n minus 1 y of n wn to the power of nk. So summation n is equal to 0 to n minus 1. In place of y of n we are writing a1 x1 of n plus a2 x2 of n, then into wn of nk. You have two terms separated by plus sign here. We will multiply and separate the summation. So you have summation 0 to n minus 1 a1 x1 of n wn to the power of nk. a1 I'll write it outside because it is a constant. x1 of n wn to the power of nk. Similarly we'll get a2 x2 of n wn to the power of nk. So a2 I'll write out of the summation. N is equal to 0 to n minus 1 x2 of n wn to the power of nk. So this is equal to a1 summation x1 of n wn to the power of nk is x1 of k. a2 summation x2 of n wn to the power of nk is x2 of k. So y of k we got it as a1 x1 of k plus a2 x2 of k. This is linearity property. What does linearity property say? DFT of weighted superposition of inputs is equal to weighted superposition of individual DFTs. Next is circular symmetry of a sequence. So let us consider x of n. It is a finite duration sequence of length L less than n. It is a finite duration sequence. Samples L less than n. Then we will find out xp of n, which is periodic repetition of x of n. That is, it is a periodic sequence of period n obtained by periodically extending x of n. So we can write xp of n as summation L is equal to minus infinity to infinity x of n minus ln. Then dft of x of n will be equal to dft of xp of n, because xp of n is just periodic repetition of x of n. Now we shift xp of n by k units, and I'll represent that signal as xp dash of n. It is xp of n minus k. That means xp of n shifted by k units. So xp of n is represented by this summation. So xp of n minus k will be summation L is equal to minus infinity to infinity x of, wherever n is there, I'll write n minus k minus ln. So the periodic sequence xp of n, it is shifted by k units to the right because we have used n minus k, and we are getting xp dash of n. Now this xp dash of n is also periodic repetition of some sequence, that is shifted version of this periodic sequence. So from this we will take n samples from the first cycle, so, and that I'll call it as x dash of n. So x dash of n is equal to xp dash of n, and we have taken the samples from 0 to n minus 1, and all other values of n we will take x dash of n as 0. What does this mean? X dash of n is a finite duration sequence because it contains only n samples. So it is a finite duration sequence, and this will be related to our original signal sequence x of n by circular shift. X dash of n and x of n related by circular shift. Now we'll see what the circular shift is. Let us take one example to explain this concept. So we have x of n, which is finite duration sequence. So let me take one finite duration sequence. Let us say it has got 4 samples. Let the sample values be 1, 2, 3 and 4. This is our x of n. Next we have periodically extended x of n to get xp of n. So xp of n is periodic repetition so it is periodic repetition of x of n. So this is xp dash of n. You can see 1, 2, 3, 4 periodically repeated. After every 4 samples. Next, what we are doing is we are shifting this sequence xp of n by k units. So let us take okay, this is xp of n. So now this will be xp dash of n, which is xp of n minus, let us say we are shifting it by 2 units. So when we shift by 2 units, what we are going to get? 2 units means each sample is shifted by 2 units to the right because it is xp of n minus 2. So the sample 1 which occurred at n is equal to minus 4 will now occur at minus 2. So we have shifted the sequence by 2 units towards right. Now what we are doing is we are taking 0 to n minus 1. N is here, 4 samples are there. So 0 to 3 we are taking the samples and taking it as x dash of n. So n is equal to 0 to 3. In this window, whatever samples we get, those samples we are taking. That is, we have got 3, 4, 1 and 2. These samples we are taking and we are labeling it as x dash of n. Now how x of n and x dash of n are related to each other? I told you they are related by circular shift. So the circular shift, we actually represent the sequence in circle. So let us take original sequence x of n. This is position 0. Only 4 samples are there. So position 1, position 2, position 3. And the samples are 1, 2, 3 and 4. Now we will draw x dash of n, which is x of n minus 2. So again position 0, position 1, position 2, position 3. But what are the values? We have 3, 4, 1, 2. This is 3, 4, 1, 2. Now when I look at x of n and x dash of n, we come to know that in anti-clockwise direction, when the sequence x of n is shifted by 2 units, see this one, that means you are turning the knob in anti-clockwise direction. Let us say by 2 units you are shifting. Then this one, it has gone by 2 positions. So position 1, position 2. So we got 1 here. 2 has shifted by 2 units, which way it was in position 1. Now it will come to position 3. The sample 3 which was at position 2, now it has come to 0. Sample 4 which was in position 3, now it has come to position 1. So from this, what do you understand? X dash of n is nothing but x of n shifted by 2 units in anti-clockwise direction. Because I have written the samples in anti-clockwise direction. Okay, so original sequence x of n we have drawn, then the sequence x dash of n we have drawn, and x dash of n is nothing but circularly shifted version of x of n, and x of n circularly shifted by 2 units that we have got. So I hope you have understood this concept. So how do you represent this circular shift? Circular shift x dash of n, this x dash of n, it is represented as x of n is shifted by 2 units circularly. So we write it as x of n minus 2 modulo n. So in general, this is x of n minus k, because k units, by k units xp of n has been shifted. So x of n minus k, we call it as x of n minus k modulo n, and this is equal to x of n minus k plus capital N. That means whatever is there in this bracket plus n we have to do. So x dash of n is in general x of n minus k modulo n, which is x of n minus k plus capital N. So here in this case k is equal to 2, so we have x dash of n is equal to x of n minus 2 modulo 4. So this is equal to x of n minus 2 plus 4, or x of n plus 2. Now when you substitute n is equal to 0, I'll get x dash of 0, that is equal to x of 0 plus 2, or x of 2. And what is x of 2? X of 2 is 3. So this is equal to 3. Next, if I substitute n is equal to 1, I'll get x of 1 plus 2, that is x of 3, and x of 3 is 4. So 4. Next, x dash of 2 is x of 2 plus 2, that is x of 4, and x of 4 is nothing but x of 0, 1, 2, 3, 4. It is circular, so x of 4 is equal to x of 0, that is equal to 1. And x dash of 3 will be equal to x of 3 plus 2, that is x of 5. X of 4 is nothing but x of 0, and x of 5 is nothing but x of 1, and x of 3 is 4, x of 4 is equal to x of 0 is equal to 1, x of 5 is equal to x of 1, that is 2. So x dash of n we got 3, 4, 1, 2. You can check, we had got 3, 4, 1, 2. So in general we write x dash of n as x of n minus k modulo n. Now we generally take counterclockwise or anti-clockwise direction as positive direction. So if in the normal linear shift, if I take x of n minus 2 to be shifted right, that is right side is considered positive and left side is considered negative. Same way in circular shifts, anti-clockwise direction is considered as positive and clockwise direction is considered as negative. Now if an endpoint sequence satisfies the condition x of n minus n is equal to x of n, if this condition is satisfied, then we call such sequence as circularly even. Whereas if x of n minus n is equal to minus of x of n, then we call such sequence as circularly odd. That means when x of n minus n is equal to x of n, they are symmetric in nature, and circularly odd sequences means they are anti-symmetric about the point 0 of the circle on the circle. And circularly folded sequence is nothing but reversing the sequence. Circularly folded sequence is nothing but x of minus n modulo n, or you are finding out the reverse, time reversed sequence of x of n, and this is nothing but x of, I told you, whatever is there in the bracket, add n to that, so this will be x of n minus n. So if you consider an example, if the input sequence is x of n equal to 4, 6, 8, 6. Then if I plot it on the circle, this is 0 position, first position, second position, third position. So 4, 6, 8, 6. 4, 6, 8, 6. I'm writing x of n in anti-clockwise direction. You can see that position 1 and position 3, the samples are same. And the condition for this is 1 less than or equal to n less than or equal to n minus 1. For this one also it is 1 less than or equal to n less than or equal to n minus 1. Similarly, circularly odd sequence means x of n, if it is, let us say 4, 6, 8, minus 6, you can see that these two values 6 and minus 6, they satisfy the condition x of n minus n is equal to minus x of n. So this sequence is circularly odd sequence. So next is symmetry properties of the DFT. So let endpoint sequence x of n and its DFT be complex valued, or in other words, x of n can be written as xr of n plus jxi of n. It is complex valued. Similarly, x of k also we can split into real and imaginary parts as xr of k plus jxi of k. Now when you take the DFT formula, x of k, which is xr of k plus j xi of k, is given by summation n is equal to 0 to n minus 1 x of n. So x of n, I'll write it as xr of n plus j xi of n into wn to the power of nk. Wn to the power of nk is e to the power of minus j 2 pi nk by n. So this is given by summation n is equal to 0 to n minus 1 xr of n plus j xi of n into e to the power of minus j theta can be written as cos theta minus j sin 2 pi nk by n. Now we will multiply and split the real and imaginary parts. So xr of n multiplied with cos theta and jxi of n multiplied with minus j sin 2 pi nk by n, we will get the real parts. So we'll get xr of n cos 2 pi nk by n, j into j minus, minus into minus plus, so I'll get plus xi of n sin 2 pi nk by n. This is the real part out of x of k. So this summation n is equal to 0 to n minus 1 of whole of this is xr of k. Now multiplication of xr of n with minus j sin and jxi of n with cos, we'll get imaginary part. So I'll separate the summation and accordingly write. And then we'll get xi of k so here xi of n into cos 2 pi n k by n minus xr of n sin 2 pi n k by n. So the first term gives xr of k and the second term is xi of k. Similarly, so I'll write this separately here. xr of k is equal to summation n is equal to 0 to n minus 1 xr of n cos 2 pi n k by n plus xi of n sin 2 pi n k by n, and xi of k is equal to summation n is equal to 0 to n minus 1 xi of n cos 2 pi n k by n minus xr of n sin 2 pi n k by n. So we'll write this as equation 1 and 2. Now take the IDFT formula. X of n is equal to 1 by n summation k equal to 0 to n minus 1 x of k e to the power of j 2 pi n k by n. So this can be written as 1 by n summation k equal to 0 to n minus 1. X of k can be written as xr of k plus j xi of k. E to the power of j theta will be cos theta plus j sin theta. Now once again we will multiply and separate out the real and imaginary parts. So xr of k multiplied with cos and jxi of k multiplied with j sin, it will give xr of n. So I'll get 1 by n summation k equal to 0 to n minus 1 xr of k into cos 2 pi n k by n. J into j I'll get minus xi of k sin 2 pi n k by n. And then you multiply xr of k with j sin and xi of k with cos, you will get imaginary term, that is xi of n we will get. So plus 1 by n summation k equal to 0 to n minus 1. I'm multiplying xr of k with xr of k with sin and xi of k with cos. So xi of k with cos and xr of k with sin 2 pi n k by n. So here xr of n is 1 by n summation k equal to 0 to n minus 1 xr of k cos 2 pi nk by n minus xi of k sin 2 pi nk by n, and the imaginary part of x of n, that is xi of n, is given by 1 by n summation k equal to 0 to n minus 1 xi of k cos 2 pi nk by n plus xr of k sin 2 pi nk by n. So I'll write these equations as 3 and 4. Now, symmetry properties of the DFT, we will consider real valued sequence. So when I say real valued sequence, that means x of n is real. So when x of n is real, then x of n is equal to xr of n and xi of n is equal to 0. Okay, so then in that case, if I consider the first two equations, you can see xi of n is 0, so this term will become 0. So in xr of k, xi of n sin 2 pi nk by n will become 0, and in xi of k, xi of n cos 2 pi nk by n will become 0. So we will have xr of k equal to summation n is equal to 0 to n minus 1 xr of n cos 2 pi nk by n, and xi of k equal to summation n is equal to 0 to n minus 1 minus xr of n sin 2 pi nk by n. Okay, and when it is a real sequence, then okay, these equations I'll write it as 5 and 6, and x of n is real sequence, then x of n minus k will be equal to conjugate of x of k. It will be equal to conjugate of x of k. So when I say something is equal to its conjugate, what does it mean? It means magnitude of the both sequences are same, and angles are like angle of x of n minus k is minus angle of x of k. So let us check when x of n is real, whether x of n minus k is conjugate of x of k. So we will take the formula of x of k, that is the DFT, and this is equal to summation n is equal to 0 to n minus 1 x of n wn to the power of nk. Now substitute n minus k in place of k, so we will get 0 to n minus 1 x of n wn to the power of n into n minus k. So from this we know it is summation n is equal to 0 to n minus 1 x of n. If I expand this, I'll get wn to the power of nn into wn to the power of minus nk. We know that wn to the power of nn is equal to 1. So this is equal to summation n is equal to 0 to n minus 1 x of n wn to the power of, I'll write minus nk as n into minus k, or this can be written as x of minus k, because in place of k we have minus k. Now similarly we'll take the formula once again and apply conjugate on both the sides. So when I apply conjugate on both the sides, the DFT formula, so I'll get conjugate of x of k, and here I'll get summation n is equal to 0 to n minus 1 x of n wn to the power of nk whole conjugate. So summation n is equal to 0 to n minus 1. This whole conjugate I'll bring inside, so each term we have to find the conjugate. So conjugate of x of n into conjugate of wn to the power of nk will be wn to the power of minus nk. So, and x of n is real, so conjugate of x of n is equal to x of n. So that's why this will be summation n is equal to 0 to n minus 1 x of n wn to the power of minus nk. So this is also equal to x of minus k. Now here what I can do is that n is equal to 0 to n minus 1 x of n wn to the power of minus nk into wn to the power of n capital N. So if I multiply with wn to the power of n capital N, it does not change the value because this is equal to 1. So this I can write it as summation n is equal to 0 to n minus 1 x of n wn to the power of n into n minus k, which is equal to x of n minus k. So we prove that conjugate of x of k is equal to x of n minus k, provided x of n is a real sequence. So this is a very important symmetric property. When x of n is a real sequence, x of n minus k is equal to conjugate of x of k, or x of k can be written as conjugate of x of n minus k. Now symmetric property when x of n is real and even sequence. So x of n, it is real and even sequence. So when x of n is real, we know that x of n is equal to xr of n, and x of n and conjugate of x of n will be same. Xi of n is equal to 0. And now here x of n is even as well. So when x of n is real, we came across these two, equation number 5 and 6, and now x of n is real even also. So when it is even, we check these sum of products. Cos theta is even, cos theta is even, sin theta is odd. Now it is given that x of n is even, so even into even will give even sequence, even into odd will give odd sequence. Summation of even sequence, it will be there. Summation of odd sequence, all the samples are going to cancel each other, and xi of k will be equal to 0. xr of k will be summation x of n cos 2 pi n k by n, but xi of k will become 0 because it is summation of even into odd. So if we take an example, like we know that in even sequences, let us say all ones, this is an even sequence. This is an odd sequence. I've just taken an example. You multiply all samples are 1. This is -1, this is +1. The sample values which you will get after product is here -1, -1, 0, 1 and 1. And now summation of the products. When we say summation of the product, all these values should be added. So you can see that summation of the product of even and odd will be 0. So XR of k is equal to summation n is equal to 0 to n minus 1 XR of n or x of n, because anyway x of n is equal to XR of n, cos 2 pi nk by n, whereas xi of k is equal to 0. And because x of n is real and even, x of n will be equal to x of n minus n. And this can be proved by taking the IDFT formula. You take x of n is equal to 1 by n summation k equal to 0 to n minus 1 x of k wn to the power of nk. Now in place of n, substitute n minus n. Summation k equal to 0 to n minus 1 x of k. In place of n, we are writing n minus n into k. So this is 1 by n summation k equal to 0 to n minus 1 x of k wn to the power of nk into wn to the power of minus nk. We know wn to the power of nk is equal to 1. So we get 1 by n summation k equal to 0 to n minus 1 x of k wn to the power of minus nk. So we can write it as x of minus n. And x of minus n will be equal to x of n, because x of n is a even sequence. Next, if the sequence is real and odd, that means x of n is real and odd. Real, so x of n will be equal to xr of n, and xi of n is 0. And it is odd sequence. Odd sequence means x of n is equal to minus of x of minus n. Then in that case, x of n will be equal to minus of x of n minus n, which can be proved by using the IDFT property. And another thing about xr of k and xr of k is summation of x of n into cos theta. Xi of k is summation of x of n into sin theta. So here now because x of n would be odd, or summation of odd into odd, odd into odd will become even, like positive numbers we will get. So this summation holds good, but summation of x of n into cos theta, odd into even, this summation will become 0. So XOR of k will become 0, Xi of k will be present. So XR of k will be 0 and Xi of k will be equal to minus summation k equal to 0 to n minus 1 x of n sine 2 pi n k by n. Next, when the signal is purely imaginary sequence, that means x of n is equal to xi of n. xr of n is 0. Then in such case, we have the formula from equation 1 and 2. Here xi of n is there, xr of n is 0. So that means xr of k will be summation xi of n into sin theta and xi of k will be summation xi of n into cos theta. So xr of k will be summation xi of n into sine and xi of k will be equal to summation xi of n into cos. So if xi of n is even, then sin theta is odd, so xr of k will be 0 and x of k will be equal to xi of k. Whereas if xi of n is odd, then cos theta is even, so xi of k here it will become 0 and x of k is equal to xr of k. What does this mean? If the input sequence is purely imaginary and even, then we get imaginary DFT. DFT will be imaginary. Whereas if the input is imaginary and odd sequence, then the DFT is real. So here this is imaginary even sequence, DFT is imaginary, purely imaginary. If the input sequence is purely imaginary and odd sequence, then the DFT will be real sequence. Similarly, when x of n was real and odd sequence, then we had got x of k as purely imaginary. That means xr of k was 0 and xi of k existed, so it was purely imaginary. Whereas if x of n was real and even sequence, then x of k was real, because xr of k existed and xi of k was 0. So this is about the symmetric property. Next, circular convolution. The convolution property of the DFT, it states that multiplication of the DFT of the two sequences is equivalent to DFT of circular convolution of the two sequences. So if x1 of n, the endpoint DFT, gives x1 of k, and x2 of n, the endpoint DFT, gives x2 of k, then circular convolution of x1 of n and x2 of n. So this symbol indicates circular convolution, or you can also write the symbol instead of n with a circle, you can write as star with a circle. Only star means that is for the that symbol is indicates linear convolution. So star with a circle indicates circular convolution. Excuse me. Then the endpoint DFT will be x1 of k into x2 of k, and the circular convolution is given by, if I consider this as x3 of m and this as x3 of k, x3 of m is equal to summation n equal to 0 to n minus 1 x1 of n x2 of m minus n modulo n. This is the formula of circular convolution. So we have to prove that circular convolution of the two sequences in the time domain is equivalent to product of the individual DFTs in the frequency domain. So from this, let us take x1 of k equal to summation n equal to 0 to n minus 1 x1 of n wn to the power of nk, and x2 of k is equal to summation. I have already taken the variable n here, so let me take the variable l. So l is equal to 0 to n minus 1 x2 of l wn to the power of lk. Then we have x3 of k as x1 of k into x2 of k. So we'll find out x3 of m, which is IDFT of x3 of k. So 1 by n summation k is equal to 0 to n minus 1 x3 of k wn to the power of, I have used m here, so mk. Now here 1 by n summation k equal to 0 to n minus 1 x3 of k is x1 of k into x2 of k wn to the power of mk. So we will substitute the value of x1 of k and x2 of k in this. So we will get 1 by n summation k equal to 0 to n minus 1. Instead of x1 of k, we will write summation n is equal to 0 to n minus 1 x1 of n wn to the power of nk, that is x1 of k formula we are writing, into x2 of k formula we will write, that is summation L equal to 0 to n minus 1 x2 of L Wn to the power of Lk into Wn to the power of Mk. Now all summations we will bring to one side. So we will get one by n summation n is equal to 0 to n minus 1 x1 of n summation L is equal to 0 to n minus 1 x2 of L, then summation k equal to 0 to n minus 1 and Wn to the power of all these terms. I'll take k common, I'll get n plus L plus M. Wait a second. IDFT formula I had to put a minus, sorry for that. So please change here minus. So here I will get minus. So x3 of m is equal to 1 by n summation, we have taken n is equal to 0 to n minus 1 x1 of n summation L is equal to 0 to n minus 1 x2 of L and summation k equal to 0 to n minus 1 Wn to the power of k n plus L minus 1. Now this is of the form summation k equal to 0 to n minus 1 a to the power of k. We can write it as 1 minus a to the power of upper limit plus 1 by 1 minus a. A is equal to Wn to the power of n plus L minus M. So separately if I take this summation k equal to 0 to n minus 1 Wn to the power of k into n plus L minus M, then I can write this as 1 minus a, so Wn to the power of n plus L minus M to the power of n by 1 minus Wn to the power of n plus L minus M, right, because we are substituting this value of a in this formula. Now Wn to the power of anything into capital N is 1, so 1 minus 1 we will get a 0. When does this occur? When this Wn to the power of n plus L minus 1 is not equal to 1. Okay, so we have to check condition for which this will be equal to 1. When n plus L minus M is multiple of capital N, then Wn to the power of n plus L minus 1 will become Wn to the power of Pn, which is equal to 1. So in that case the denominator will become 0. So this is of the form 0 by something. So this answer will be equal to 0 when the condition n plus L minus M is not equal to Pn. We have considered Pn because multiple of n. It is not a multiple of capital N. then 0 by some denominator you will have, answer will be 0. But if n plus L minus m equal to Pn, that means if it is equal to multiple of n, then we cannot take this for answer of the summation, because 0 by 0 you are going to get. That's why we are going to replace n plus L minus m as Pn in original summation formula. So this will be equal to 1. Summation of 1, we will get it as n. When will we get n? When n plus L minus m equal to Pn. Then in that case this summation will be equal to n. So anyway, when it is not equal to integral multiple of capital N, it is 0. So 0 means whole everything will become 0. But only in this condition this whole summation x3 of m will exist. So x3 of m will be equal to 1 by n summation n equal to 0 to n minus 1 x1 of n, x2 of, we will write L. When I say n plus L minus m is equal to Pm, L is equal to Pn minus n plus m. So I'll substitute that m minus n plus Pn, and this summation of Wn to the power of kn plus L minus n, I'll replace it with n. So this n and this n cancels. So this is equal to summation n is equal to 0 to n minus 1 x1 of n x2 of m minus n plus Pn. So we get x3 of m is equal to summation n equal to 0 to n minus 1 x1 of n x2 of m minus n plus Pn. Now what is this x2 of m minus n plus Pn? It is, that is x2 of L is equal to, we have written it as x2 of m minus n plus Pn. So if I expand, it is this is integral multiple of capital N. So if I substitute p equal to 0, I'll get x2 of m minus n. If I substitute p as 1, I will get x2 of m minus n plus capital N. If I substitute 2, I'll get x2 of m minus n plus 2n. Or if I substitute minus 1, I'll get x2 of m minus n minus capital N, etc. And all these values are equal, and we can write it as x of m minus n modulo n, because you can see that it is periodic repetition of x2 of m minus n. So we can write this as x2 of m minus n modulo n. x2 of m minus, it indicates x2 of m minus Pn is periodic sequence of period n, and x2 of m minus n minus Pn is x2 of m minus n plus Pn is delayed version of x2 of m plus Pn, that is circularly shifted by n samples. So that's why we can write this as x2 of m minus n modulo n. So we substitute in the previous step. So x3 of m is equal to summation n is equal to 0 to n minus 1 x1 of n x2 of m minus n modulo n, and this is the circular convolution formula we got. So circular convolution in the time domain is equal to product of individual DFTs in the frequency domain. So the circular convolution of two sequences requires that one sequence should be periodic. If both sequences are non-periodic, then periodically extend one of the sequences and then perform circular convolution. and when we perform circular convolution on two sequences, both will have same number of samples. And let us say if the length of the sequences are different, then to the smaller sequence you have to append zeros or add zeros such that the length of both the sequences are same. And we can, in short, we can find out the circular convolution of the two sequences by making use of matrix method. You can see that one sequence is circularly shifted and multiplied with another sequence and summation of the product. Whenever we have summation of the product, then you can represent it using matrix multiplication. So here x3 of m, that is x3 of 0, I'll take an example of n is equal to 4. So x3 of 0, x3 of 1, x3 of 2, x3 of 3 we are going to get by circularly shifting one sequence and multiplying with another sequence. So x2 of 0, x2 of 1, x2 of 2, x2 of 3 circularly shift. So this you just shift here, x2 of 1, x2 of 2, x2 of 3. Now once again shift 3, 0, 1 and 2, and finally once again shift x2 of 2 here, x2 of 3, x2 of 0, x2 of 1. So we have circularly shifted. When n is equal to 4, 4 cross 4 matrix you are going to get circularly shifted one, or n cross n matrix, and that will be multiplied with the other sequence, that is x1 of 0, x1 of 1, x1 of 2 and x1 of 3. So when you multiply circularly shifted sequence with the second sequence, you will get the circular convolution. So this is the by using matrix multiplication we can find out the circular convolution. So anywhere summation of products we have, we can represent it using matrix multiplication. So other properties we will prove in the next video lecture. I hope you have understood the 5 properties which we have proved till now, and we have learnt the formula of circular convolution. Circular convolution of two sequences is given by summation of n is equal to 0 to n minus 1, x1 of n, x2 of m minus n modulo n. I hope you remember linear convolution of two sequences. The formula was y of n is equal to summation k equal to minus infinity to infinity x of k h of n minus k, or summation h of k x of n minus k. Similarly here also you can circularly shift x2 of n and multiply with x1 of n, or circularly shift x1 of n and multiply with x2 of n. So thank you. We will continue the other properties in the next video lecture. Thank you and have a good day.